Yeah, you can start.
Okay, great. So I don't know, I guess since there are a couple of new people, I'll start with introductions. Hi guys, my name is Aditya and I am currently in my sixth year of IIIT, Hyderabad. I'm a dual degree student CST and I do research in the CVIT lab. But the topic of today's seminar has nothing to do with computer vision anyway, so let's start. So this seminar is all about introduction to special relativity. And I wanted to take this seminar for two reasons. First of all, people either think that one, special relativity is too simple and only general relativity has the good stuff, or two, they just think that special relativity is a subset of general relativity and it doesn't really contain any mind-boggling facts or things about physics and the universe on its own. Now, in this short talk, I'll try to dispel those two wrong notions. So let's start. And so we'll start by giving an overview about space-time. So where does our story start? Our story starts in measurement. So consider, what do I mean by measurement? Let's say you're living on a flat world, two-dimensional world. We're not talking about time right now, and you want to create a map. You're a surveyor and you want to create a map of the earth or some piece of land you're living on or whatever. What do you do? What you can do is you can, whatever you want to measure, you can put a mark or a tripod or something, some rod or some marker in the ground to mark that place, and then you can similarly mark many other places, and then you can perform measurements between those two things. That is one way. The second way, which is the more physics way of doing it, is you make measurements based on your reference frame. And what do I mean by a reference frame? Think you in the two-dimensional case, you can think of a reference frame as the graph. You are the observer at the origin, and the various stakes and markers that you put on the ground at various places are the points on your graph. So, and now what is the goal of physics? So the goal of physics is to make measurements, predictable make predictions about the universe and share them with others and communicate them with others and let others verify them. So what problems do we run into here if we use this approach? First of all, we need a way to relate quantities measured in one frame of reference to another frame of reference. What do I mean by this? I guess we should have some pictures over here. Okay, this is screwed up. Yeah, so this is what I mean. Forget all the other things for now. This is our graph, and these 4 points are ABCD here and ABCD here. The problem is that each individual, this individual and this individual, will have his own system of measuring things. And what do I mean by system? In this particular case, a system of measuring things consists of this axis, these two axes, and the units along these two axes. So for example, if we look at the coordinates of point A in this frame and the coordinates of point A in this frame, these two will be different. So so the numbers this observer gets and the numbers this observer gets are quite different unless you know how to change from one to the other. So this is a central sort of fact of surveying and measuring. And what useful information can we get? The useful information that we can get on the surface is of distance. The distance between two markers is always constant. So what do I mean by distance between two things? If you look at the distance between A and B here and A and B here, this will be constant irrespective of the reference frame. And so this example of things which stay constant between two frames of reference is called an invariant. In the scenario I just described, the invariant is the distance, which is simply change in the x coordinate squared. So if you had more coordinates, it will be x1 squared plus y1 squared plus z1 squared, and in the other coordinates it will be x2 squared plus y2 squared plus z2 squared. And look, and this delta sign is important. This delta is basically saying we are measuring separation, not the actual coordinates from the origin. We are measuring separation, which is this delta x, xb minus xa. Delta x here is xb minus xa. So that is what these notations mean. And similarly, when we come to space-time, the central invariant in space-time is the space-time interval, which is given by this c in the, which is the speed of light, times the time separation whole squared minus the space separation whole squared. So a couple of comments here. Why do we need invariants? So the reason we need invariants is that, you know, we need some way to relate two different sets of measurements made by two different observers in two different frames. If I give you a set of numbers and you give me a set of your numbers, we need some way to relate the two. And as we will see later on, two different observers need not measure the same spaced separation between two events, or they need not even measure the same time separation between two events. But what is the quantity that they will measure to be the same? Which this is, that quantity is the interval. So an important it gives us important information about the universe, and the key point is that this information is independent of the observer. Everything else you measure, velocity, time separation, space separation, length, everything else depends on the observer. I can change my, if I'm measuring something, the velocity of a moving train, I can change my measurement based on how fast I'm moving with respect to the ground and things like that. But this space-time interval, this is a quantity which is invariant of the observer, and hence it is important. Now, a small note about events and intervals. So what is an event in space-time? So going back to our example of surveyors on land, remember that to mark out points of land, we put markers or rods or stakes in the ground. An event is exactly like that, but in space-time. So events can be described with a coordinate, which is x, y, z, t for time, or they can be described verbally. For example, I can say um, a train moving along a track at the point at which it enters a long tunnel. And by point here, I mean full four-dimensional coordinates, x, y, z, and t. That is one event. And the point at which the front of the train exits the tunnel, that is another event. So events are to space-time what the markers and rods and physical measuring stakes were to the ground. Now we come to the concept of wristwatch time and proper time and local time. So one of the consequences of special relativity, as we will see later on, is time dilation. And what is time dilation? Time dilation is nothing but the fact that two different observers need not agree between the time difference of two different events. For example, we've all heard this classic twin paradox, which I will not get into here. But what happens is that, you know, there are two twins. One of them stays on the Earth, and the other person gets into a rocket and travels very fast to the other galaxy. And both of them carry two different clocks with them, and they measure two different times. All of that. So in this framework, there's a certain concept of wristwatch time, proper time, and local time. All these things mean the same. It is essentially the time measured by the observer for which the two events happen at the same location. And what do I mean by this? All of this will become clear with an example later on. But for now, just remember there's a concept of wristwatch time or proper time. Then the second thing is space-like versus time-like intervals. This is exactly as the word suggests. If you go back to this formula, if delta x is more than c delta t, then this entire interval is negative. So that sort of interval is called space-like. Essentially, we are saying between these two events, there is more space than there is time. And versus time-like intervals, again, if c delta t is greater than delta x square, This entire thing is positive. So that interval is time-like. Again, we are saying that between these two events, there is more time than there is space. As an example, you can say that you can consider it right now. I am taking this seminar. It starts at 5 p.m. in my local time and ends at 6 p.m., let's say, in my local time. What does that mean? As far as I'm concerned, both the start and the end happen at the same physical location, which is right in front of me in my monitor. But there's a time difference of 1 hour between them. So these two events are separated by a time-like interval. Okay. On the other hand, consider again the start of the seminar on my monitor and the start of the seminar on your monitor. Both events are happening at the same time, but they are separated by I don't know how many miles and kilometers in space. So this interval, the interval separating these two events, my start and your start, is space-like. So that is it. Now, before I move on, are there any questions? And please keep pestering me with questions and discussions because I am not used to giving talks or lectures at all. So yeah, any questions up till here? Nope. Okay, doesn't look like it. So I'll move on ahead. Now we come on to units of space and time. So space and time, the fundamental question is, why do we club space and time together into one thing called space-time? And what is this? Why does the speed of light c come into the picture here? And the one of Einstein's fundamental insights was that space and time have the same units, and the speed of light c is nothing but a conversion factor. It's like the conversion factor between feet and meters. It's an accident of history. What do I mean by accident of history? I mean that first, for whatever reason, we chose the unit of distance, which is the meter. And then later on, we chose the unit of time as the number of periods of vibrations of a certain cesium atom for whatever reason. And then we fixed the speed of light to be whatever, to be c. And why have we fixed the speed of light? For historical reasons, because this law of special relativity, and actually even before this, Maxwell's law said that the speed of light is invariant for all observers. So based on that, we made one measurement of the speed of light, and that fixed our units of meters, our units of distance and time, because we wanted that number, the speed c, to be the same and to not change after that. But what I'm trying to tell you is the actual value of the speed of c is not a fundamental constant of the universe like pi. It's not. It's like a conversion factor between feet and meters. And just as feet and meters can measure distance, meters and seconds can both measure space-time. And I felt that an example was needed over here. So when we want to convert between feet and meters, what do? We start by saying, okay, we start making a measurement and saying that, okay, 10 feet equals 3 meters. And then we get these two ratios. 10 feet upon 3 meters equals 3 meters by 10 feet equals 1. And this 1 over here is unitless. Since we're doing physics, the units are important. All right, so these two ratios are the exact same, and which give us the unitless one. It's often called unity. So let's say we want to convert 3.14 feet into meters. What do? We perform this calculation. We want to knock out meters. We multiply with 10 feet upon 3 meters, and then we crunch the numbers, and it gives us 0.95 feet. Similarly, in the space-time case, what we say is that 1 second equals c meters. So basically, we are saying that if we measure distance and time in the same units, be it meters or seconds, the speed of light is 1. Does that make sense?
I think someone has a question.
Okay, 1 second.
Yeah, so I still don't get what you meant when you said that C is not a universal constant like pi is.
Okay, so
And
okay,
I didn't understand
right.
your statement when you said the other
Hmm.
thing as well, as to how we use
Hmm.
the same measurements for speed, for time and space.
This distance, right? Okay. So first of all, what did I mean by say that? So I didn't say. So what I meant was pi tells us something about the nature of the universe. It's a geometrical fact. Whenever we draw a circle, the ratio of the circumference to the diameter is pi. That constant is independent of the observer. It's a fact of geometry. Okay, the value of pi, 3.14 dot dot or whatever, is a consequence of geometry. All right. It's not a consequence of our measurement units or anything. Whereas c, the speed of light, c, the actual value, is a consequence of the fact that we use different units for space and time. Okay. It's
Yeah, I
like
get it.
saying,
Yeah, I got this
yeah,
part.
yeah. So it's like saying this. Before, when we had just space, we had coordinates x, y, z. We measured all of the coordinates x, y, z in meters, right? But for some reason, when we move to space time, we measure our coordinates in x, y, z, t. And through an accident of history, we've been measuring x, y, z in meters and t in seconds. And as a consequence of this accident of history, when we measure the speed of light, we get a number which is something, something which is c, which we represent by c, meters per second. And as we will, and as this example shows, you can use the same you can use the same units as well. So again, let's do the same calculation here. 1 second equals c meters, and so the ratio 1 second by c meters and c meters by 1 second is a unitless quantity 1. Cool. Now if you want to convert 3.14 seconds to meters, we go through the same calculation. This time 3.14 seconds is multiplied by 3 to 10 power 8 meters upon 1 second, and then it gives us 9.48 to 10 power 8 meters. That's it. So what I'm trying to tell you is that I can talk about meters of time and seconds of time and meters of space and seconds of space. To drive home this point, I have another example. So let's consider an example. A proton moving at 3 by 4th of light speed passes through two detectors in a laboratory placed 2 meters apart. The events E1, E2 are the transits through the detectors. Okay, so now what is the interval between the two events? So first of all, we said that the interval between two events is an invariant. We can measure it either in the proton frame or in the lab frame. So we all of us know what is the lab frame. It is the frame of reference attached to the laboratory room. What is the proton frame? With respect to the lab, the experimenter, what he or she will see is that, imagine a set of coordinate axes whose origin is at the proton, and those axes are moving with the proton. So that frame can be imagined to be the proton frame. Of course, the proton doesn't, if you were the proton observer, if you were attached to the proton frame reference, you would not see your own axis move, of course not. But that is just to get an imaginary idea in your head of what a frame of reference is. Cool. So now what is the interval between the two events? First thing we do is calculate the lab time between the two events, which is distance upon speed. So we get 2 meters by 3c by 4 meters per second. I don't know if I should zoom in further. Okay. I saw
Yeah,
there's something in the
it's
chat.
fine.
I'll address it later. And so this gives us 8 by 3 seconds of time, which is 8.89 into 10 power minus 9 seconds. Now, what I've been trying to tell you is that seconds and meters are interchangeable. It's just a conversion factor. So just like we had uh, 3 meters by 10 feet is a unitless one, we have uh, we have c meters by 1 second as a unitless one. So again, I can do the same here. 8 by 3 c seconds into c meters by 1 second gives me 8 by 3 meters of time. This meters of time can be slightly confusing, but again, the thing to remember here is that meters and seconds are just units, and distance and time can be measured in the same units. So then after that, it's pretty simple. The interval is the same in the proton or the lab frame. So we can measure it in the lab frame, which is the delta t squared minus delta x squared, which gives us 3.111 meters squared. Right. This is the square of the interval in the lab frame. And now let's say we want the time in the proton frame. Okay, so again we use the same equation that we gave above. The intervals are invariant. So what is the interval in the proton frame? Proton time squared minus proton distance squared. And when I say proton distance, I mean that the distance traveled by the proton as measured by the proton, which is of course 0. So for the proton, the two events, the entry into one detector and the entry into the second detector, happens at the same place. The space separation between them is absolutely 0. And so it measures a certain time, and based on this math, you can get proton time equals 1.764 meters of time. Just for sake of clarity, I have converted meters to seconds here, and it gives us 5.88 into 10 to the power minus 9 seconds. And so what does this tell us? In the lab frame, the measured time interval between the two detectors was 8.89 into 10 to the minus 9 seconds. Whereas in the proton frame, it was 5.88 into 10 to the minus 9 seconds. So this is a clear example of time dilation. We will move on to formal methods of conversion and the Lorentz transform later on, but this is a clear-cut example of time dilation. And why does time dilation occur? It occurs because the only invariant across frames is this interval, delta t squared minus delta s squared. Delta t itself is not a constant, and delta s itself is not a constant. So if two observers do not agree on the space separation between two events, according to the proton, the space separation is 0. According to the lab experimenter, the space separation is 2 meters. If they don't agree on the delta x, the space separation, they will not agree on the delta t, which is the time separation. And this simple fact is all there is to time dilation as far as special relativity is concerned. Now, the second comment I wanted to make here is that space and time have the same units, but are not completely the same in quality. What do I mean by this? If you look at this formula here, even though all these quantities have the same units, we are adding something, adding the time and subtracting the distance. So in a certain sense, the space and time dimensions are being treated differently. They have a different quality as far as the metric. This formula for the distance is called a metric. It's called a space-time metric, and this is technically called the Minkowski metric. So this metric treats the dimensions t and x differently, but since it is just adding or subtracting things, the units have to be the same. So okay, so and another thing I wanted to mention here is that this factor of c only appears when you're measuring time in seconds and space in meters. So this is the formula in SI units. If you want to measure everything in the same units, be it meters or seconds or years or feet, yes, we have feet of time as well. We can have that. This factor of c goes away, so it just becomes delta t squared minus delta x squared, which is what you would have seen in a lot of textbooks. And now, before I move on, I should take a look at the questions. C is can you just tell me or clarify a question again? C is something we use as a base, or we're assuming a constant and building a theory around it. Can you just explain to me that question again? I think I missed it. Okay, it's okay now. All right, cool. Any other questions?
Yeah, I have a question.
Yeah, sure.
Yeah, so to the last point that you're saying as to how they are different in quality. So, so for example, when I think of distance, I can imagine a path, right? Because that is a quality of distance.
Right.
So when
Okay,
you measure two things
so
in the same,
just 1 second here. When we say distance, we just mean the separation, and separation is independent of path. That's all I'm saying. So if I go back to this example, even though the path between them can take whatever, but we are just measuring the distance between them as in the separation based on the coordinates. So you just do coordinates of b minus coordinates of x. That's all. This notion of distance is
oh, so
based
distance
on
here is
coordinates.
displacement.
Yeah, it's displacement. Yep.
Okay, okay, yeah.
Yeah, that's it. So yeah, essentially we are working with coordinates here, and all of these things, time and distance, delta time and delta distance are just coordinate differences. That's all. So they are independent of the path taken between them actually. Cool. So let's move on. Now, okay. So now measuring space time. Okay. So how do we measure space time? Given that there is time dilation, how do we measure things far away? So the challenge is this. Let's right now. I just said that okay, you and I are viewing this screen and viewing this seminar at the same time, but at two different places. So how do I measure, how do I make sense of this phrase at the same time? Whose whose clock is measuring this time? So that is a question which we need to formally answer, and here is how we do it. So just as we had a graph paper with a coordinate system in the 2D case, we have a certain grid of clocks and rods, imaginary grid of clocks and rods in our 3+1 dimensional case, three space and one time. So I think uh, mm, I think an image here should be helpful. Nope, 2.4. Yeah, and this image, a lattice work of meter sticks and clocks. So let's say I am here. I am an observer. I am standing here, and what I have done is that created this lattice of meter sticks. Each sub each of these rods and sticks is 1 meter in length, and each of these clocks is identical to the clock here. And how do I go about building this lattice work in an imaginary sense? So I start here, I move one, I place a rod, I go to the end of the rod, I align my next rod, let's say this one, with this one to be parallel to this, and then I just put it. And by repeating this process, I can place all the rods. All right. Now, how do I um, place my clocks? What I mean by this is I have a bunch of clocks with me in a bag at this point. What I want to do is place all the clocks at these various points. So what is the most naive method? You just put your reference clock here, you take the entire bag with you and put another clock here. But notice what you're doing. You're moving along this with some speed, right? You're moving along this distance with some speed when you're setting this lattice up. And what does that mean? Since I am moving with some speed here, I will actually experience time dilation. And what is actually time dilation is just the fact that since the intervals are constant, if I don't agree on the distance separation, I will not agree on the time separation. What this means is that the very act of constructing this constructing this imaginary reference frame will make my clocks go out of sync. The zero of this will not be the zero of this. So how do we so now, which gives us a new problem. Suppose we are able to arrange this entire setup of rulers and clocks with by traveling at some speed and putting our clocks and rods here. What we need to do is now that the clocks are no longer synchronized. Okay, so what do I mean by that is if I were to go to this place and bring back this clock somehow at the same speed or whatever, somehow this clock will now measure a different time than this. So initially, even if all of the clocks measured 0, and then I took this clock here and I arranged everything and I brought this clock back, the time measured by this clock and this clock will be completely different because we have traveled at a certain speed. Now, one thing we can do is that we can travel at a very slow speed, but no matter how slowly we travel, unless we travel with a speed of 0, which is impossible, our clocks will always go out of sync. So now our problem of constructing this framework has been reduced to a problem of coordinating all the clocks. So how do we coordinate? Well, we have a useful phenomena at hand. So Maxwell's laws tell us that the speed of light is invariant in all reference frames. So what I can do is say that okay, after I've arranged my reference frame, I've arranged all my rods, I've arranged all my clocks. What I do is this: at my t is equal to 0, I send out a light pulse from my reference traveling in all directions. Now, this observer here, when this light pulse reaches this observer, it sets its own time, this clock, to 1 meter of distance, because the separation between these two things is 1 meter. So light has traveled from here to here. It has traveled a distance of 1 meter. So the time separation this needs to measure is also 1 meter, because light travels at a constant speed irrespective of the observer. So this clock knows that, okay, since light has traveled from here to here a distance of 1 meter, in my reference frame, meaning I should measure the time taken from here to here to be also 1 meter of time, which is 1 by c seconds. And similarly, if you're talking about this clock, the separation between these two things is root 2 units of distance, let's say root 2 meters. So when this light pulse reaches here, it will set its own time to be equal to root 2 meters of time, which is root 2 by c seconds. And so this is how we can construct our entire framework. And now all the clocks are now all the clocks are coordinated using the universal light pulse. And now we can talk about things happening at two different places at the same time. What do I mean by that? What do I mean by that? What I can do is this: imagine each clock has a recording facility, local recording facility. It can record the timestamp of events which happen around it. All right, so right now imagine this entire framework spreads all across the earth. And when I say events are happening at two different places at the same time, what I mean is this: let's say the event E be me clicking my mouse on the screen. This is the origin, and you are measuring a different time here. And you are seeing this click here. What I mean by the same time is that this clock and this clock will measure the same time. And how do I measure it? So let me see if I can make this a bit clearer why we need this. All right, okay, so the observer here can't go all the way there to measure it, because one observer cannot be in two different places at once. But what we are saying is that this entire lattice work is the observer. And what do we mean by this? Let's say this event happens here. What is the time of this event? It is the time as recorded by this clock. Let's say, and the event happens here. What is the time of this event? It is the event as recorded by this clock. So if these two clock recordings agree, if these two timestamps agree, they are the same, then we say that this observer, which is represented by this lattice, has observed two events at the same time. I am pretty sure there are a lot of questions here. Nope. Does this make sense? Because this was pretty complex for me when I first saw it. Cool. Seems fine.
Again, like,
yeah.
Briefly.
Somebody had a question?
Yeah, me. Could you go over that again? Like.
Okay. So all right. So first of all, do you understand why we've done this?
I kind of got the I didn't get the click example that you gave, as in taking the whole
Mhm.
lattice as an observer. Why would you take the whole lattice as an observer? And even if you do take the whole lattice as an
Mhm.
observer, both the clocks are within the observer then, right? So,
Okay, so all right, so let me ask you a question. Imagine this is the Earth, and this is the star Alpha Centauri in the next in the other galaxy. So I send a spaceship from here to here. All right, cool. And I ask you, what is the time it takes to go from here to here? Right, and the time as measured by the observer sitting on the Earth. How does this observer measure the time from here to here? In theory, in practice, it will be obviously different, but in theory, how does this observer measure the time it takes for the rocket ship to go from here to here?
mhm, speed of the ship by distance.
Speed of the ship
Distance,
by
distance,
distance.
distance,
Okay.
distance between the Alpha Centauri and Earth by speed of the ship.
How do we measure the speed of the ship?
Um, Not sure.
Assume the speed of the ship is variable. We are not controlling this experiment. We are just observing the motion of the spaceship. How do we then do it?
We take a reference and probably divide the entire distance into discrete intervals, something like that.
Hmm.
And then we measure the time gap it takes to cover each discrete interval and then add those up to get the total time. Would that work?
Yeah, that is essentially what we are doing. Even though I have said that these are unit distances, when we make a graph, we have a bunch of small little squares, and in theory graphs are infinite resolution, right? And by that I mean we can, even though the board lines are 1 unit apart, we have smaller subdivisions, and in theory we can have even smaller subdivisions. So when you say uh, divide that entire path into small distances and add up the delta t's, that is exactly what we are doing. And why can we do this? Because we have this framework of clocks and rods. So when you say, just to answer your question, you said that we can divide, let's say, this distance into small subdivisions and add up the delta times. So how do we add up the times? I now ask you that. Let's say I have this path, the spaceship moves along this path, and you say that, okay, we divide this path in small chunks. We measure the time separation in each chunk, and we add up the time separation. So I ask you again, how do we measure the time separation in each chunk?
We'll need a reference, which probably
What is a reference?
something universal, like the speed of light. Like that's the reference we all use, right?
Exactly. So here also we are using the speed of light as a reference. We are saying that, okay, I will send out a pulse of light, and then based on my pulse of light, you fix your clock reading. So when my pulse reaches here, my clock should read 1. When my pulse reaches here, my clock should read root 2. So this framework allows us to measure exactly what you're asking me to measure without dividing into small chunks and without physically going there, because I already have a clock over there in theory. Does that make sense?
Okay, so what you're doing is calibrating everything according to the clock you're sending the light pulse from.
Yes, this is my reference. So just like we have a reference origin, we have a reference clock at the origin.
But you were talking
Hmm.
about taking the lattice as an observer. What were you trying to say there?
Okay, so what am I trying to say? Okay, think of a lab. Okay, and you have a think of a lab and you have a long track, and then you can start the stopwatch when something enters one end of the track and stop the stopwatch when something leaves the other end of the track. Correct?
Yeah,
In this sense, you are the observer,
yeah.
right? And you could do this because you could observe both ends of the track, quote unquote, at the same time or almost at the same time. The time delay for you to
Yeah, yeah,
look
negligible.
at one end
We're
and
got
it
there.
is negligible. But now imagine this track was 1,000 kilometers long. Okay, and the particle or whatever the thing under observation was moving along the track at a certain speed. How would you measure the time taken now? Let's say you know the distance beforehand. How would you measure the time taken now? One way would be, okay, uh, one way would be, when the trolley or the train enters the track, you start your stopwatch, and from there on start running, and trying to keep pace, and start running and keep pace with the train, and when it hits the other end of the track, you just stop your stopwatch.
Yeah.
Okay, but is that the same time that will be measured by somebody who is, by some observer who could see both ends of the track at the same time? So in this sense, okay, go back to the lab example. Imagine, you can observe both ends of the track at the same time, correct? So you can make that measurement, right?
Yeah.
Imagine there was an ant who could only see one end of the track, and it takes that ant a finite amount of time to go from one end to the other end. Now if that ant did what we did in the long track case, which is it started its stopwatch, ran with the train, and then stopped its stopwatch, would you trust that time measurement to be the same as yours?
Now that we know a little about time dilation, no.
Yeah, exactly. So now that we know about time dilation, this is exactly why we are making this entire series of things. So just to go back to the lab example, let's say there was no omniscient observer. Let's say you were not an omniscient observer who can measure things at the same time with no time delay, yada, yada, yada. How do we do it? We are the ant. What we can do is we can set this up. We can set up this framework beforehand. What I can do is, okay, let this be the track. For what I measure out the distance. I take two clocks, let's say this and this, and um, I set both clocks to, okay, I don't set it to zero right now. What I do is I ensure that both clocks are identical. And when I say identical, I mean they tick at the same rates. Cool.
Yeah.
Then I put one clock at one end, I take the other clock at the other end, put it there and come back. Right.
Mm-hmm.
Now, since we know something about invariance of the interval and time dilation, this clock, the reading on this clock will no longer agree with the reading on this clock.
So you send a light
Right?
pulse to calibrate them again.
Exactly. We send a light pulse to calibrate them, which means
Okay.
at t is equal to 0, I send a light pulse from here, and
You said that it equals 1 or whatever. Yeah, you said that it equals 1.
at t is equal to 1 based on the known distance. This clock sets its own time through some mechanical contraption or whatever. Now what I do is, when my car or when my train enters this track, I click this clock, observes it and records the timestamp,
Yeah.
and let's say prints out a time. When the car exits, this clock prints out the time here. I later on I compare these two pieces of paper, I compare the timestamps, and then I calculate the speed and make my measurement. So essentially, even though one person or one observer cannot be at both ends, right, this system of lattices is doing the observation and making the recordings of the timestamp for the observer. So that is what I meant when I said that the lattice is the observer.
Okay, since the lattice is like the collective framework of all these clocks, both these clocks are within the lattice, so it is like an omniscient observer here.
Yes, exactly.
Oh,
It is like saying I can stop the stopwatch at both ends of the track with no time delay. I am omniscient. I can go from here to there instantaneously, and all of that.
okay, so it's like God observer.
Yeah, exactly. And if you think about it, all observers in physics are God observers. It
Yeah,
doesn't
because
make
everything is
sense to
ideal
talk about.
in these cases.
Yeah, exactly, exactly.
Thank you.
Cool. So now we move on. Yeah. So events at the same place versus at the same time. So now we move on to free float frames, and they are also called inertial frames. And inertial frame is any frame in which a law of inertia applies. What is the law of inertia? An object will not change its velocity, zero or non-zero, unless acted upon by an external force. Correct? So any frame in which the law of inertia applies is a free float frame. And what do I mean by this? Wait 1 second. I believe we are running out of time. Yes, consider this example. All right, let's say I am an observer in this box, and this box, I have constructed this and that my entire lattice in this box, and I throw a ball with certain velocity from here at t is equal to 0. Now, if the law of inertia were to apply, all right, what should I observe? That this ball should keep moving in a straight line, but it doesn't. What I see is that this ball takes this curved parabolic path. Now, since we know a bit about gravity and we are outside this box, we can say that, okay, the earth exerts a force of gravity on this, and then this curves, and that is why it deviates from the straight line path. Okay, but we don't want to do that. Why? Because within the confines of this box, there is no earth. There is no source for this force and this deviation on this, or deviation from ideal straight line motion of this ball. So what do we say? We say that this box is not an inertial observer because the law of inertia does not hold in this region. How do we fix that? We simply say, okay, go along with gravity, go in free fall. If we go in free fall, we will see that the ball goes along the straight line path. Correct? Now, is the motion of the ball changing? Absolutely not. As this infographic tries to tell you, it's the same ball at the same place at the same time. It's just that by virtue of our own motion, we have changed the apparent motion of the ball. It still obeys the same laws of physics. It is just that since this observer is inertial, it can see the um, law of inertia in action. There is no source of a force on this ball that this system can see, and also the ball follows a straight line path. Its velocity is constant, whereas here its velocity is not constant. So any frame of reference or any observer for whom the law of inertia holds is known as an inertial observer or a free float observer or a free float frame. Is that clear? Speed will be relative, right, to time. Yep. So speed is relative, and whenever I say speed, I mean speed as relative to me. Since I'm the one doing the measurement, I'm saying speed relative to me. So we are replacing distance measurements with time. We're not replacing distance measurements with time. It's just that since we've already laid down our meter rods, we know the distance a priori, and we are replacing time measurements by comparing the timestamps of the two clocks. Okay, that's to answer the previous question. Are there any? Yeah. Okay. Cool. Are there any questions regarding this free float frame thing? Okay, I assume no. Moving on. Okay, so I'm going to skip these 2 points about locality of frames. Not really important, and in the interest of time. So now we move on to special relativity. What does it say? It says that all inertial frames are equivalent. Means an observer can verify physics by making observations from his or her own frame and staying within the frame. And all inertial observers will see the same laws of physics. Okay, what does this mean? Let's say let's say there are two long parallel train tracks, and there are two different cars moving along the tracks at two different velocities with respect to the ground. What special relativity is saying? All inertial frames are equivalent, right? It means that both of these, if there is an observer making some lab experiments within the boxes, both of these boxes will see the same outcomes. They will measure the same physical laws. All the measurements and all the laws of physics that they come up with will be the same. Physics will be the same for both these inertial observers. And more importantly, there is nothing that the observer within the box can do to calculate their own speed with respect to the ground. So this is important. What do I mean by this? Let's say, going back to this example, forget gravity for now. Imagine this is just a straight track and my entire box is going at a constant velocity with respect to the ground, and it's just moving along like this. Now, no matter what, and I am confined inside this box, no matter what I do, no matter what measurement, what experiment, no matter what experiment I do, no matter what observations I make, I can never ever calculate my velocity with respect to the ground. Okay. And why can't I do that? If that would happen, it would violate special relativity, because imagine again, there are two different inertial frames moving in this direction with two different velocities with respect to the ground. Okay, I conduct experiment A here. I get the value of my speed v with respect to the ground, and this person conducts the same experiment A here and gets their value of speed with respect to the ground, let's say v1 and v2. Since the outcomes of the same experiment are different, relativity has been violated. Because why? We just said that all inertial frames are equivalent. All right, so there is nothing the observer in the box can do to figure out their own speed uh, with respect to the ground by making experiments within the box. So that is also an important consequence of the principle of special relativity. And so this brings us to the only mathematical part of today's seminar. Before I move on, are there any questions?
Yeah, sorry.
Yeah, go ahead, please.
Um, Going back to that two cars example. So now let's say we have this experiment that takes a known amount of time. Hello?
Okay. Yeah, okay.
Yeah,
What do you mean known amount of time? Known amount of time with respect to whom? The experimenter in the lab frame.
Yeah, the experimenter, if he starts the experiment, when the experiment ends, he'll know how much time has passed.
Okay, and
That's
you're
what I'm
saying this time frame is a characteristic of the experiment, and
Yeah, it's a
like, yeah,
characteristic
that's
of the
it.
experiment.
Okay, cool.
And both the observers in both the cars know this experiment.
Mm-hmm.
And now both of them conduct the experiment.
Right.
And when both the experiments are over, they'll know the time gap between them, right? Like the time that's passed.
Okay, so no, how will they know? How will they know that there cannot be any? There are two different isolated systems, right? So box one is a system, box two is a system. If you want them to communicate, they're no longer two different systems. They are just one larger system, and you need one larger observer to talk about this, right?
Oh yeah, because okay.
Yeah. So that's what I meant. So I meant within the confines of this box.
Hmm.
Okay. Just for completion, what was your point?
No, I kind of wanted to say, why can't both of them measure their own individual speeds and get done with it by using? But then I myself noticed that they won't have a measure of distance. So what will they do even if they do measure?
Right, and also they won't even be able to measure their own individual speeds, because how will this guy measure?
Yeah,
Okay, let's say
exactly.
there are some markers alongside the track. We'll have to look outside his system for this. So by definition, his experiment is not within the confines of
Yeah,
his
it's not
frame of reference.
isolated then.
Yeah, exactly.
Hmm.
And so yeah, his the word I was looking for is it's not within his frame of reference. And what I mean by this is I skipped over these 2 points, is that frames are local in nature. They are restricted in both time and space. So when I say that this is the box, I mean that my inertial reference frame only extends up to this boundary. It doesn't exist outside. And what I mean by that, I've just skipped over, but you can read through the book for that point. But the point is that when I say frame of reference is local, I mean that beyond this square, the law of inertia does not hold anymore. And an observer will observe deviations from the law of inertia if my frame was this big. Okay, so now moving on. Yeah, sorry, does that answer your question first of all?
Yeah, it does. This is like we're kind of exploiting the fact that it's an isolated system and that any contact with the
Yeah.
external system would just make it an extended system. Okay.
Yeah, exactly. Okay. Also, can we use the left diagram as an example? Since it's not inertial, but for the purposes of my most recent discussion, this was inertial. I'm not considering gravity. I was just saying, like I said, these are just two different train tracks, and these two boxes are moving with some constant velocities, but different velocities down. That's all. Yeah, you're right. But I'm not using the diagram. I made a few other assumptions and I've stated that. So I believe that answers your question. And final thing, okay. Now we come to the actual Lorentz transform, and which implies some math. So what is a transform? Before we answer that question, let us look at how we've been doing physics all this while. So if you look at this formula, where did it go? Yes, all it talks about is about separations between things, right? It doesn't tell you, if I give you the raw coordinates of one point in this frame, and I tell you, give me the raw coordinates of this point in the other frame, you will not be, this formula alone will not be enough to tell you. For that we need, and which is why we need a Lorentz transform. So a transform of this sort is useful because we don't always have events to mark out locations in space-time. So this is like saying, okay, I don't have stakes to put in the ground on a map, but I still want to do surveying. I still want to measure the coordinate of a certain thing and be able to tell the other guy, okay, this is what the coordinates of the same thing are in your framework. So that is what this Lorentz transform does for us. And it's the setup is very simple. We have two frames of reference, O and O dash, and x, y, t are the coordinates in O, and x prime, y prime, and t prime are the coordinates in frame O prime. O prime or O dash is the same, right? And x, y, t, we can also have x, y, z, t, and whatever. So for the purposes of this derivation, what I have done is that O prime is moving with respect to O with speed v along x-axis. The speed v is with respect to O. X-axis is x-axis of O. And further, I am saying that the frames O dash and O coincide, which means that their axes are parallel. The x-axis, the y-axis, the z-axis, they're all parallel, and the time axis of both the things are all parallel. Does that make sense, or do I need a diagram for this? Everyone? Does everybody understand when what do I mean when I say O and O prime have axes parallel?
I got it. So
Yeah, okay, cool. All right. Now, since we say that, okay, O prime is only moving with respect to O along x-axis, this is what my equations become. Instead of, even though I have more y and z coordinates, they will not change because my only motion is in the x prime direction. And this paragraph basically says why we can just drop this equation since there'll be no change. So now this is what I need to do. I have x prime as a function of x and t, and t prime as a function of g and t, where x and t are measurements made by O, and x prime t prime are measurements made by O prime. And these measurements are not separations, they are full-fledged coordinates. All right, now, and also again, these two things are linear. Both of these observers, O and O prime, are inertial observers. So this is how the derivation proceeds. Step one, we show that the functions f and g are linear. Why are the functions f and g linear? Because, for example, if x prime dependent on, let's say, higher powers of t square and t cube, this person would observe an acceleration. And since we said that both observers are initial, you cannot have one person cannot observe accelerations of the other frame. So now our equation is reduced to this: x prime equals ax plus bt and t prime equals cx plus dt. We could add constants here, but we are saying that both the origins coincide, which means at t equals to 0, the origin of O and the origin of O dash are at the same place. So basically, I mean that 0 of x comma 0 of t equals 0 of x prime comma 0 of t prime. So that's what I'm saying. So 0 0 in O equals 0 0 in O prime. So we are reduced to these equations. Now step 2 is derive the change in the x coordinate. So we use the fact that O prime is traveling with velocity v with respect to O. This means that any point stationary in O prime will be observed by O to have velocity v independent of position and time. Okay, so consider x prime equals to k. What does this mean? This means that there is some object at x prime equals to k which is stationary with respect to O prime. And I perform the substitution, ax plus bt equals k. Now I get x equals minus b by a t plus k by, which is another constant. If I differentiate this, I get v dx by dt equals minus b by a. And but what is dx by dt? Dx by dt is just v, because like I said, x is the coordinate of this point which was stationary. And since O prime is moving with velocity v, anything that is stationary in O prime should have velocity v in O. Where is O? In O. So I can replace dx by dt by v. So I get b equals minus a v, right? Now I do this. Our position transform now becomes x prime equals a into x minus vt. Since we are trying to derive a general transform, the same equation must also apply in the reverse direction. So now what I said was O prime is moving with respect to O in with velocity v, and for that the transformation becomes x prime equals a x minus vt. On the other hand, if I say, I can also equivalently say that O is moving with respect to O prime with velocity minus v. So I get two equations, x prime equals a x minus vt and x equals a x prime plus vt prime, where I have made the appropriate substitutions in the opposite direction. Cool. Next, we use the invariance of light speed, which is a consequence of Maxwell's laws. And again, like I said, both inertial observers should observe the same laws of physics. So both should agree on the fact that light speed is invariant. So specifically, imagine a light flash from the common spacetime origin. O observes the trajectory of this flash to be x equals ct, and O prime observes the trajectory to be x prime equals ct prime. Why? Because both observers must agree on the same speed of light c. We've used the fact the velocity of light is independent of frames. Now, up till now, we haven't used any invariance of intervals right now. We are just using physical laws, and substituting that into the above two equations, we get this. From here, it's a bit of math where we multiply them together and we get the value of a as 1 by under root 1 minus v square by c square, which is the usual factor gamma. Our final position transform now becomes this: x prime equals gamma x minus vt. Now, out of the two equations, we have one equation done. Now the second thing, again, we use the invariance of light speed, and we use the fact that x prime equals ct prime and x equals ct must hold simultaneously. But instead of substituting in the x equations, we substitute this in the t equations. So we make the substitutions here. So ct prime equals gamma ct minus vx by c is equal to this, and t prime is equal to gamma t minus vx by c square. And how did we get this? We made the substitutions: x prime equals this, x equals this, and t equals this in the first equation alone. So x prime equals ct prime, gamma goes to gamma, x goes to ct, and v into t goes to v into v into x by c, and this gives us t prime equals this. But notice that we said t prime equals cx by dt, and since these two equations must hold simultaneously, because this is a general transform and this is the equation of the trajectory of a particular flash of light that we are measuring. So these two equations must hold, which gives us c equals minus gamma v by c square and d equals gamma, which gives us our final transform. X prime equals this and t prime equals this. This is the actual final Lorentz transform that is quote unquote world famous by now. Does anybody have any questions till now? I'm guessing there are no questions, and yeah, that is the end of my seminar today. I hope you guys learned something and weren't too hindered by my lack of experience in teaching.
It was really fun, like, to be honest.
Cool. Thanks, that's good to know. Yeah, and that's why I like it, right? Because people think that, oh, to appreciate physics and to appreciate the universe, you need a lot of math, and there's a bunch of complicated stuff. But no, it isn't. What did I start off with? I just said that, look, nothing is constant except for this, and Maxwell, which is another physical law, tells us that speed of light is constant, and you get pretty interesting stuff on its own. And here we have no gravity, we have no acceleration, it is just inertial observers. All the things that you've seen later on, in terms of rocket ships and accelerations and bending of light, all of that is all general relativity. So we don't even need to go there to you know appreciate how interesting things are.
Yeah, and it was also
I,
like really surprising here for me when you just cut off everything and you just say all inertial frames are equivalent and you isolate the systems. How much you really can't do at that point.
yeah, exactly.
It's like we're almost exploiting the fact that all inertial systems are equivalent, and somehow that really feels nice. Not sure why.
Yeah, it is. So yeah, that's it, right? That is what it is. That is what we mean when we say using this law of physics. We are literally exploiting that law of physics
Yeah.
to figure things out. Yeah, I think Anirudh, that's it. So you can stop the recording.
Yeah.
Thank you so
Thank
much.
you very much for the talk.
Cool. Thanks, guys. Thanks for